Well, good morning. So what we've done so far is that we've gone through a sequence of different kind of stimuli and applied them to the system. So when we started looking at time-varying things that change with time, we started with looking at the impulse responses and step responses, these transition. And that led to the operator analysis. That led to the Heaviside operator that we've extensively discussed and gone over. Now, and then we saw that there was another kind of stimulus that we can actually apply, which was the e to the st kind of things, right? E to the st's led to essentially the system functions, or you could also say that they led to Laplace transform. That's how we arrived at those. Now, and last time what we started doing, we started looking at the phasors, basically looking at sine and cosine stimuli. Now we are getting to things that are more practical in the lab, right? From things that are more idealized, like impulses. And when we saw that you could actually look at define each sinusoid essentially with two parameters, its amplitude and phase. Or you could think about them as a sine and a cosine added with different weights, which would be a Cartesian representation of what the amplitude and phase would be a polar representation of. Right? So there are two different things. They actually are called later on, that's cosine and sine are called I and Q, in phase and quadrature. You will see them a lot in communication systems. We refer to them constantly as I and Q, IQ systems, things of that sort. So they refer to in phase and quadrature, which is the cosine and sine in that order. So cosine is in phase. Now, and then what we did, we started talking about the Bode plots. So what were the Bode plots? So we'll spend more time today on Bode plots because they're important in several different ways. So what we said from an experimental perspective was that if you had a system you wanted to characterize, so let's say you had this box, and this was in the lab, for example. So you had a box, and it had an input and an output. So you applied some sort of an input to it, let's say, so this is some ground, this is some actual waveform, so let's say it's a signal generator, and it generates some sinusoidal waveform. So let's just do it this way. And then you take the output of the system, and then you connect it to an oscilloscope that would show you the waveform, for example. So this is the oscilloscope, and it has its knobs and controls and things of that sort. And what it does, so it basically, you take a probe from the oscilloscope, and then you come and look at the output here, and then you compare it, you take another probe, and you put it connected here, so you see both the input and output at the same time on channel 1 and channel 2, for example, if you're using, from a very practical standpoint. And when you do that, when you look at the screen of this oscilloscope, so let's say if I magnify the screen of this oscilloscope and put it here, what you really see is that you will see two sinusoids, right? You will see the input sinusoid, and if it's an LTI system, so let's say this is an LTI system for now, you will see an output sinusoid, which would have it would be at the same frequency, but could have a different amplitude and a different phase. But these are things that you can measure. So as you change the frequency of this thing, so f0, or if you look at the angular frequency, which is 2 pi f0 omega naught, you basically can look at this time difference and translate it. So if you have a delta t here, that delta t over t0, which is the period, so this being t0, times 2 pi is the phi at that particular frequency, right? And the ratio of this amplitude to that amplitude is essentially the magnitude of this thing. Now, the Bode plot, we argued, is essentially a plot of these two quantities as you change the frequency. So it's nothing other than that. So its importance comes from the fact that it can be also, one of the significances that it has comes from the fact that it can be evaluated experimentally. So you can do it as a function of omega, and what you actually plot is really, what you do is you measure it in dB. Now, what is dB? Or let's say measurement of dBs, it's measured in Bell. Bell is ratio of powers, the log base 10 of ratio of powers. So the units of little case kind of Bell is ratio of powers usually the output to input, or 10 log of that, let's say. I'm sorry, just log of that, log base 10 of that, not 10 log. Log base 10 of ratio of powers is Bell. Now, if you have ratio of power, of course, now we want to kind of like since we said Bell could be used to be a difficult or like a large unit, so you'd look at the decibel, which is 1/10 of that, which becomes 10 times log base 10 of ratio of powers, let's say P2 to P1. And if you're looking at ratios of voltages, ratios of powers are usually proportional to the ratio, powers are proportional to voltage squared, right, for a fixed resistor. So then you get 10 log base 10 of, let's say, V2 squared over V1 squared, and that being a log, this squared comes out, becomes a factor of 2, so it becomes 20 log of V2 over V1. So if you start measuring voltages, you really need to plot 20 log of the ratios of the output voltage to the input voltage. So that's what we call, that's why we show this as the magnitude part of it as 20 log, really base 10, of magnitude of h of j omega. That's why we look at 20 log of that, and that becomes dB. So it really comes from the fact that you're looking at the log base 10 of the ratio of powers, and then you're using a smaller unit, decibel, so that gives you the 10, and ratios of power are proportional to the ratios of voltages squared, which gives you the 20. And then you're also looking at the phase of that. So what you do, you, for example, measure the ratio of this to that, and calculate log base 10 of that, and then multiply by 20, and then you plot it. And when you do that, as you change the frequency, you will get different values here, right? So for different, and usually, also the x-axis is done on a log of omega. So it's a log-log plot for the magnitude. So this is, the x-axis is also done in log. So you will do something like this, and then you, for example, see something that does that. And then on the phase side, also you get some data points. Something like that for the system. So you could interpolate between these points and produce an actual plot, continuous plot that could look like that in this example. So you have two parts, a phase and an amplitude. Now, there are several reasons we use Bode plots. One of the advantages, as we saw last time, is that if you have cascaded systems, so how does it work for cascaded system? If you have a cascade of, let's say, 3 systems with impulse responses H1, H2, and H3, and transfer functions H1, capital H1, capital H2, capital H3, we saw that the aggregate response is H1 convolved with H2 convolved with H3 of t, which translates in the frequency domain to H aggregate frequency response, aggregate transfer function, being the product of these, as we've seen before. And since we are looking at products, here, if you look at the logs of them, you will get the sums. In other words, you can write each one of them. So another way to think about it is that h of s eventually will have these terms in the numerator and denominator. And these terms in the numerator and denominator can be written as, let's say, S1, S2, S3. These are complex quantities, right? At a given frequency. Let's say at a given j omega, at a specific a omega. And there are P1, P2, P3. So each one of these will produce these terms. This is the numerator of the first one. This is the denominator of the first one, evaluated for s equals j omega, right? This is the numerator of the second one, the denominator of the second one, evaluated for j omega, and so on and so forth. So if you think about those, what do you get? So you can write this as magnitude and phase. So you can write it as S1 e to the j, let's say, theta, or phi1, right? And then the other one is S2. You can write it in polar. Basically, what I'm doing, I'm writing them in polar representation. And S3 e to the j phi3. And the same thing for the denominator. So it can be P1 e to the j theta 1, P2 e to the j theta 2, and P3 e to the j theta 3. Now, if you look at this carefully, you can easily see that you can separate it into a magnitude part and a phase part, right? The magnitude part is magnitude of S1, magnitude of S2, magnitude of S3, divided by magnitude of P1, magnitude of P2, magnitude of P3 times. And then you get these phases. So you get e to the j phi1 minus plus phi2 plus phi3 minus theta 1 minus theta 2 minus theta 3. So you can see that the phases add and subtract. The phases of the numerator components will add, and phases of the denominator components will subtract. And you can see that the magnitudes are multiplied and divided, which basically translate in a log domain. These would be adding and these would be subtracting. That's why we do the log for the magnitude part, not the phase part. Because the phase part by itself adds and subtracts. But to make a magnitude part also additive as opposed to multiplicative, then you take the log of the magnitude part. Then makes both of them additive. So if you have a cascade of 3 systems, and if you know their Bode plots, you can basically just add the Bode plots, the magnitude part and the phase plot. Magnitude with the magnitude, phase and phase, obviously. And then you get the aggregate Bode plot. So that's an interesting aspect of it, and it's useful. So then the next thing, so that's how it's done in a lab, for example, and this is the the theoretical foundation behind it. But there's also another part. So there's a kind of like a reverse problem. Not exactly a reverse, I mean, looking at it from a different perspective, which is if you are given a transfer function analytically, if you have the analytical value of, let's say I tell you what the transfer function is. The transfer function is s plus 1 over s plus 2. Right? How do you determine its Bode plot? And this is also a valuable exercise because it allows you to see how the system responds at different frequencies. Okay? So this is what we want to be doing. So the question is, how do you do that? And then what you'll see in the next few minutes, we'll develop a couple of very simple rules that allow you to plot the Bode, get the Bode plot, do the Bode plot, by just looking at it and doing some base, applying those rules. So if you want, you can always do the brute force thing, right? I mean, which basically is saying that, so let's say, if I were to give you some transfer function, right? If I told you what h of s is s plus 1 over, and this is an example. I mean, I'm not going to solve right now, so I'm just going to use it as an example to show you something. S plus 2 over s plus 3, right? So you can always plug set s to equal j omega and say, okay, well, this is 1 plus j omega over 2 plus j omega times 3 plus j omega, and calculate the magnitude. So this is h of j omega. And calculate its magnitude, right? You multiply by its complex conjugate, and then you get its magnitude, some function in omega, right? Which in this case would be 1 plus omega squared over 4 plus omega squared times 9 plus omega squared, right? So that would be the magnitude of this thing. And you can also calculate its phase. For that, you need to simplify it to make it that it has one j part and one part, and you look at a tangent inverse of that and evaluate it for different frequencies and put it into a computer program to plot it, and you can always do that, right? So that's a brute force way of doing it. Your computers can do it for you. But there are rules that allow you to plot these without actually going through all this exercise and get an accurate representation of what Bode plot looks like. So let's talk about, let's derive those. So how do we derive those? So again, the reason we want to do this is that Bode plots allow you to deal with cascaded systems. They allow you to have additive behavior for cascaded system. And also they give you a very large dynamic range. Now, do you know what dynamic range means? Who knows what dynamic range means? Dynamic range is basically the range of you can think about it as the ratio of the largest signal to the smallest signal that your system can handle. Now, if you had an ideal system, a perfect ideal system that we've shown, then the dynamic range would be infinity, right? Because you can have as large a signal as you want or as small a signal as you want, and that wouldn't cause any problem. But there are limits on both high end and low end of the system. So what are those practical limits when you think about a real system that produce a dynamic range? So what is the limit on the high side? What makes it not possible to have as large a signal as you want handled in your system? Think about it, a real system. Yes? You can only supply so much power. Sure. Yeah. Why? Why is that? Okay. So yeah. Go ahead.
Dielectric breakdown.
Breakdown, an example, right? But so the thing is that now, how about a passive system? Can a filter, which doesn't generate, where the output signal is not greater than the input, the output power, let's say, is not greater than input power. I hear your argument about the energy, right? So your argument is an energy, say, well, there's no infinite energy available, so I can't really produce more. But what if I had a system that the output has less energy than input? So there's no need for the system to produce the extra energy. So as long as I am able to provide it to it, it will tax a certain amount of it and then return the rest of it to me. So that energy argument, that's why I'm saying that the energy argument may work for certain things, but it doesn't. But there are things that dielectric breakdown is an example. But dielectric breakdown is an example of a more general things that can happen in real system that violates one of the assumptions that we had when we started with talking about LTI system, which is the L part of it, right? Which is linearity, right? So the system can become nonlinear, right? So there are nonlinearities in any real system, and nonlinearities limit how large a signal you can actually handle. So that's basically the upper end of the dynamic range in a real system. Now, what is the lower end? What determines the low end of the dynamic range? Why can't I deal with the arbitrarily small signals in a system? Yes? Noise. Yes, exactly. Right? Noise. And noise, as you will see later on, not in this class, but later on, you will see that noise, there are different kinds of noise. There's the so-called interference, which is basically comes from the outside, but there's something that's more fundamental and physical, which is what we call the inherent intrinsic noise. For example, thermal noise is because of the physics of the device, with the fact that electrons move around and they have random thermal movement. You remember when we talked about Ohm's law, for example, right? You remember we talked about this random thermal movement. So this random thermal movement produces some random fluctuation, which is called the thermal or Johnson noise. And that noise is essentially responsible for creating enough signal that at some level you can't go below that. So that's the noise level of the system. That determines how low you can go. So any real system has a dynamic range, the ratio of the highest to the lowest. Now, when you deal with logarithmic plots, it allows you to deal with large dynamic ranges of signals. Because you can go to ratios of like hundreds of thousands or a million, but you're going at like 60 dBs or 70 dBs or 100 dBs, 120 dBs would be ratios of power ratios of 12 orders of magnitude power difference, right? Or 6 orders of magnitude of amplitude difference, 60 dB. So that's another advantage of this thing. Those are interesting discussions, but it's a little bit beside the point. So anyway, so now let's go and try to find the rules that allow us to find what the Bode plot of a transfer function is. So let's start with something simple. So let's start with something that looks like k s to the power of n. So what does the Bode plot of a k s to the power of n look like? And we'll see that this is kind of like a unit that we'll use for subsequent things. So let's think about that. So there's a magnitude. So whenever you have a Bode plot, you have log of omega, you have 20 log of h of j omega magnitude, and then you have the phase of h of j omega. Right? So how does that look like? Well, let's look at it. So whenever you're looking at Bode plots, you're looking at specific kinds of s, right? You're looking at sines and cosine, which corresponds to s being j omega. More accurately, you're looking at unity magnitude exponentials, e to the j something, as stimuli, right? So, which can be written as sums of sines and cosines. So s equals j omega. So if I plug that in, what is the magnitude of this thing? So it basically becomes k j omega squared, to the n, and you're interested in magnitude of that. So it's magnitude of k times magnitude of omega, so it's omega n squared, times magnitude of what? Magnitude of j to the n. What's the magnitude of j to the n? Right? Why is it 1? That's correct. Why? Right, because j to the n, think about it. J to the 0 is 1. Right? J to the 1 is j, this vector. J to the 2 is, it's a rotation when you take it to a power. J to the 2 is negative 1. J to the 3 is negative j. It's a 90-degree rotation every time you add an extra j, right? So then j to the 5 is here, j to the 6, they're all on the unity circle. So it's the magnitudes are all, you can think about them as e to the 0, j0, e to the j pi over 2, e to the j pi, and e, well, let me write them in the right place. So this is e to the j pi over 2, this is e to the j pi, this is e to the j 3 pi over 2, and so on and so forth. And this is e to the j 2 pi. Right? So the magnitude of that part is 0. So we don't have to worry about it. So this is what it is. So this is the magnitude of h of j omega. So h of is k omega to the power of n. So how does that look like? How does that look like on the magnitude part of it? Well, it depends on n, right? So if n is 0, what do you see? Just a constant, obviously, right? You see a flat line. What do you see if n is negative 1? You see a line dropping this way. Remember, it's a log-log plot. It's 1 over omega, right? What is the slope of 20 log of that when n, let's say, is equal to negative 1? So for n equals negative 1, what does 20 log of h of j omega magnitude look like? So it's going to be 20. In general, it's going. So for in general, that's before you get. It's going to be 20 log of k plus 20 log of omega n squared, which gives me n times 20 log of omega. So if n is negative 1, it basically drops at what rate? 20 dBs per decade, right? Because it's log base 10. So every time you go a factor of 10 up, when you go from omega to 10 omega, if this were 10 omega to omega, if this was 10, this log becomes 1, right? And then they get 20. So the slope is negative 20 dBs per decade. This is an important number to remember, that for a single, for n equals 1, so this is for n equals negative 1, really, is you have negative 20 dB per decade. For n equals 1, you get something that grows with frequency. The magnitude will grow at a rate of 20 log, 20 dBs per decade. A decade is a frequency going up by a factor of 10, right? That's the meaning of a decade. So if I go up 2 decades, it means that I've increased the frequency by a factor of 100. So that's one. The other one that's often used is an octave, right? What's an octave in frequency? When you go up an octave, what do you do to frequency? By a factor of what?
8.
No, 2. It comes from music, right? I mean, if you think about it. Although I know oct means 8, right? So that, but it means a doubling of frequency. And why is that? Why is it called an octave? Because in well, I guess it's more of the Western musical system, which comes from a Greek breakdown of the notes. So it basically, if you look at it, it starts with 7 notes. You have the do, re, mi, fa, sol, la, ti. And the 8th note is do again. So the frequency of that second do, the fundamental frequency of the second, I guess that would be a C and lower C and up the next C, C1 and C2, it's double the frequency of the lower one. Now, there's no reason to divide it into 7. There are different ways, there are different musical systems that break it into different number of notes between that. But in this system, because the 8th note is also the same note, but it's just double the frequency, it's called an octave. That's the way the name octave is. So how many dBs per octave would it be? So if I double the frequency, what would I get here? So this is one log it's worth remembering. What's log base 10 of 2? No, it's not 6. First of all, it has to be smaller than 1, right? Obviously. It's 0.3. It's 0.3010299. Not that it's useful, but it's easy to remember because I remember that it was almost 0.3010. It's a palindrome. And then I remember it was a little bit less than that. So anyway, the rest of it is useless. So it's, for all intents and purposes, it's 0.3. So when you get 0.3, then you multiply by 20 of times 0.3. That's how you get the 6. So you get 6. So this is equivalent to 6 dBs. And it's not exact because this log is not exactly 0.3. It's a little bit more, but it doesn't matter. It's very close per decade. Oh, sorry, per octave. So it means that the magnitude of the Bode plot drops 6 dBs if you double the frequency for something like this, or increases depending on what n is. Now, if n is 2, then you get negative 40 dBs per decade, or 12 dBs negative 12 dBs per decade. So this should be also negative 6. Now, if n is 3, you get plus 60 dBs per decade, or plus 18 dBs per octave. Right? So that's the slope that you get for that. How about its phase? So the magnitude part was fine. The phase part is basically what I erased, which I shouldn't have. So I'll do it again. So the phase is essentially the part that we had that generates the phase is the j part, right? So you have j to the n determines your phase. And you remember, this was e to the j0. This is e to the j pi over 2, e to the j pi, e to the j 3 pi over 2. So the phase that you get has to be one of these 4, right? Depending on the n. So if n is 3, which one would you get? This, or that? Which one is n3? The one looking down. Yes, exactly. I see you pointing downward. So that's good. So you get 3 pi over 2, or negative 200, or 270 degrees, right? So if n is negative 2, what is the phase? This way, which is, in degrees, would it be negative 180 or 180? So the phase, so in this example, what would the phase be if n is negative 1? You're going negative 1. So it's negative 90 degrees, which is also 270, because it's a modulo 360 or modulo 2 pi. So the way you show it for negative ones, obviously, because it's a lagging phase, you show it as so you start from here. So it's basically, in this case, it's going to be negative 90 degrees. But it can be any of these 4 levels. 0, negative 90, negative 180, negative 120, negative 270 degrees. So it produces a fixed phase. So this tells you how, and there's one more thing. Where is this relative? Because we have shown the slope and everything, but we haven't said where it is relative to the other. So if omega is 1, let's say this is omega of 1, which means that log of omega is 0, right? So at that frequency, what is the magnitude of this thing? It's easy to see. What is this term? 0, log of 1, right? 0. So it's basically 20 log k. So this point is really 20 log k. So you know where it is. So you know the slope and you know where the relative height, so then you know exactly where this line falls. And then you know its phase. So this is essentially the key ingredient of producing the rest of them. If you understand this well, the rest can be built off of this key unit. That's your 2x4 Lego block. Right? Okay, so now, all right, so we've done this. Any questions on this? Yes?
Isn't this just for one n? So like would you have to like plot different n values, or is it like a different plot for every?
It's a different plot for every n. So I just basically try to do something general. Okay, good question. So it says, is this for any n or no? This is a general form of what ks to the n looks like for a given n. So in this case, we've plotted it for n equals 1. Let's do it for another n. Let's do it for, you tell me what it is. Help me out. So this is 20 log. This is the most annoying thing about the Bode plot, writing 20 log base 10 of j, magnitude of h of j omega. I wish I had a stamp. Yes, yes, exactly. Just bam. Or even better, I wish I had a stamp for the whole Bode plot, the axes and everything. Just okay. So what does that look like? Well, why don't you help me? If since you asked a good question and since no good deed goes unpunished, yeah. But let's figure it out together. Okay, so n is 2. So let's talk about the magnitude part first. So is it going to go up or down? Going up, right? Exactly. And what's the slope going to be? 40 plus 40 dB per decade, exactly. Which is also, if you wanted to express it in per octave, what would it be? 12 dB per octave. Yes, very good, thanks. And then how about the phase part? 180. So usually we look at these like in the negative ones. We can do the positive. That doesn't matter. 180, negative 180 and 180 are the same. So it should be actually plus 180 in this case if you want to really correctly do it. So I just basically changed I have two different origins for this one and that one. So it's just two plots that are plotted next to each other. So you can think about another x-axis here. Yeah. Or there. Sometimes it's just the same one. Okay? Yes? N is 2. Plus 2. So yes. Okay. Is it clear? I mean, it's not really earth-shattering, but it's just the element that allows you to do the rest of them. Okay, so let's do something a little bit more interesting. Just a little bit, though. So let's do 1 plus tau s. Now, in terms of, if this were the transfer function, what is this what are the poles and zeros? How many poles, how many zeros do you have in this transfer function? It's a single zero, right? Exactly. It's just single zero. At what frequency? Negative 1 over tau, exactly. So, okay, so how does this look like? So first of all, we are really not looking at that. We're looking at this if you're talking about Bode plot. Right? S being j omega, because it's a very special kind of perturbation. It's not any generalized frequency. It's really specific. It's like sines and cosines, really. Now, this thing. So we can look at this and say, well, how does that look like on a Bode plot? But let's look at two special cases. And this is what you do with Bode plots. You generate asymptotes. And once you know all the asymptotes, then you can generate the plot very easily. So what are the asymptotes? So let's think about two different cases. When tau omega is much smaller than 1. This product is much smaller than 1. In that case, what does this look like? So then h of j omega is almost 1, right? Because this term doesn't matter. So, and then the Bode plot of 1 is not that difficult. What is the Bode plot of 1? The magnitude part of it, let's first say. So again, this is my stamp, 20 log base 10 of h of j omega. And this is the magnitude of h of j, the phase of h of j omega. So the magnitude part of it, what does it look like? So if this were my transfer function, what would it look like? What does it look like? Transfer function of 1, n of 0 over there, which is flat line at 0 dBs, right? Because in this case, just basically it's 20 log base 10 of 1. I put the 0, it's fine. I can basically define my 0 dB to be anywhere I want. So let's start defining it here. So this is one asymptote. It means that at very low frequencies, my Bode plot should approach this line at small omegas. How about very large omegas? So think about the other end of the spectrum. If tau omega is much greater than 1, then my h of j omega is roughly what? J tau omega, right? 1 doesn't matter. And then I'm reduced to what case? Of n being equal to what? Corresponds to n of 1, right? Positive 1. And what does that look like? Well, you know what? I made a mistake. Let's put my 0 dB a little bit lower. Let's just keep it here. So this is 0 dB. So this is my first asymptote. And my second asymptote, so now this second asymptote, what does this look like? We've already done something very similar to that. So it looks like one of these, except for the fact that since n is 1, it would go up at 20 dBs per decade, plus 20 dBs per decade, and the phase would be what? 90 degrees, yes, exactly. So it would be something that goes up like that at plus 20 dBs per decade, which is 6 dBs per octave. And its phase, so the phase of the blue one is also 0 because it's 1. And the phase of this thing is plus 90 degrees. So I can have any arbitrary reference. So I can say this is basically plus 90 degrees. So associated with this asymptote, the phase of this asymptote is plus 90 degrees. The phase of the other one is 0. So I know what this plot looks like in the two limits. At very high frequencies, it should look like that. At very low frequencies, it should look like that. So the exact plot looks like this. And this deviation here, by the way, where do those asymptotes meet? When the magnitude of this thing is the same as magnitude of that thing, right? So the magnitude of this being equal to magnitude of that. The magnitude of this thing is tau omega, because j has a magnitude of 1, right? The magnitude of this is 1. So this frequency is what? 1 over tau. It's really a log of that. This is a logarithmic plot, but that's what the frequency is. We sometimes show it, I mean, most of the time we show it this way, although it's a log plot, just to emphasize what it actually is, right? So this is where the two asymptotes intercept. And then what happens here is that this deviation is maximum at this point, and it's 3 dBs. You can easily show, right? Because at this point, when these two are equal, the thing looks like 1 plus j at that frequency, right? At that exact frequency, this becomes 1. So this becomes 1 plus j. What's the magnitude of 1 plus j? Square root of 2, right? And what is 20 log base 10 of square root of 2? It's 10 log base 10 log base 10 of 2, right? Because square root of 2 gives you 1/2. And 10 log base 10 of 2 is 3. So this is exact. Well, when I say exact, I mean exactly is really 3.010299 dB, which for all intents and purposes is 3. Right? So that's what it is. And now how about the phase? How do you question?
Why is, so like when we did n equal to 1,
Uh-huh.
it intersected with the 20 log axis above 0, but why does it intersect below 0 over here?
It is intersecting actually at 0, right?
No, the longitude, like
This one? Because I just assumed it's some k that's not 1. You mean you're talking about this red one?
yeah, versus like,
Why did it intercept here, right?
yeah.
I didn't say what omega is, right? I mean, so this is not necessarily omega being 0 or log omega being 0. And this could still be true depending on what value of k is. right? This is still valid. I mean, if I have a k of 20, this would be shifted up, right? So I just wanted to, I didn't say anything about its absolute. I just wanted to look at its slope. But you have a valid point in the sense that if k were 1, then this had to intercept at this point. If this were omega, log of omega being 0 or omega being 1. But I didn't make any assumptions about those anyway. Okay. Now, any other questions? All right. So now, how about the phase? So the amplitude part we basically determined. How about the phase part? So we know the phase at very high frequencies is plus 90 degrees, right? And we know that, so let's say this is 0. 0 degrees. And we know at very low frequencies, it's 0 degrees. The question is, how does it, so it must transition from 0 degree to 90 degrees somehow, right? So there should be some transition as you go from very low frequencies, you go up. What is the phase at this exact frequency? This is, by the way, called the cutoff frequency, or the 3 dB frequency, actually, sometimes. Yes? 45. Exactly. Why? 1 plus j, right? So if you think about it, it was 1 plus j at that frequency, so it's 1 plus j, 2 vectors of equal magnitude, this has the magnitude of square root of 2, and this is 45 degrees. So at this frequency, I know exactly what it is. At this exact frequency, it's exactly halfway through. So my phase, this point at this point is at plus 45 degrees. So this is plus 45 degrees. So we know it transitioned from 0 degrees to 90 degrees, it goes through that. Now, how do we know, what is it? So here's a rule for this first order response. You start from a decade below to a decade above. So meaning a decade below to a decade above means that this is basically 10 over tau, and this is 0.1 over tau. Okay, this is dying. And what you do, let me use a different color. What you do, you start from this point, you draw a straight line, and then you end at this point. You draw a straight line that goes through the 45, goes through from here to there. And again, this is not exact. There's a deviation from this. So the actual phase looks more like this. And this maximum deviation, I think, is 5.7 degrees. So if you use this approximation, this linear approximation, your maximum error would be 5.7 degrees. But that's what it is. So what we want to see is really these asymptotes. So what we would like to see is this straight line, this straight line, this straight line, this and that straight line, and knowing that, yes, there's a 3 dB here, and then there's a 5.7 degrees error there. Okay, so that's basically 1 plus tau s. How about another basic ingredient? 1 over 1 plus tau s. Now this time I want you to help me out, help me with this, because you have everything you need to know, and you've seen an example that was similar enough to allow you to draw a conclusion about this one. What do you think? So let's see. Help me out. What are the two asymptotes? Do you want to start somewhere? Let's say, Garrett, do you want to start? So what are the two asymptotes? So how do you determine the two asymptotes? So omega tau first much smaller than 1. So in that case, what is the transfer function? Yes. So in that case, h of j omega is 1, which means that, what do I plot here? At 1 or? Correct, 1 at 0 dBs. So I can put my 0 dB here. That's what I wanted to do last time. Just thinking of this example. So I have one asymptote here. Now, how about the other? What is the other end of the spectrum, if you will? Much greater than 1, right? Omega tau much greater than 1. In which case, what is h of j omega? 0. Not exactly. Then it loses all its frequency dependence, right? We want it to be much greater than 1, but still we want to see its frequency dependence, right? So it means that 1 doesn't matter. So it becomes 1 over j omega tau, which you can also write as negative j over tau omega, right? So what does that tell you about the other asymptote? What's the slope of the other asymptote? Okay, so this is like this is still of this form, right? For what n? What's n? Negative 1. So what do I have? What's this asymptote? The slope? Negative 20 dBs per decade, yeah. And what is this intercept point? What is omega? When this is equal to that, right? Which is omega as 1 over tau, correct. So these are the two asymptotes. How about the phases? The phase associated with the first one. What is the phase associated with the first one? The blue one. 0 degrees, right? This is 0 degrees. And what's the phase associated with the brown one? Negative 90, exactly. So negative 90 degrees. Well, let's put it here. Negative 90 degrees. And what is the phase exactly at this point? 45? Negative 45, yes. So this is going to be negative 45 here. And where do we start if you want to have the transition, since it's the first order transition? A decade below to a decade above. So we start from 0.1 over omega, let's say it's here, to 10 over, I'm saying negative 1 over tau to 10 over tau. And then you transition with a straight line here and there. And we know that there is a deviation here. Actually, I did this incorrectly here. It's on the inside. Looks like that. It's this deviation is here, and it's on the inside. I plotted it incorrectly. And then how does it look like here? The actual plot looks like this. If you look at your books, you'll probably find much better quality graphs than mine. But then again, they haven't done it with hand on the whiteboard. So, okay. So that's what it looks like, right? So this is the Bode plot. So it looks pretty complex, but because we have put a lot of details on it, but it's really the asymptotes that matter. This asymptote, that asymptote, this transition of the phase. So if you use all these, just what we have so far, let's do a couple examples. And then we'll see that we need something else. We need to develop one more thing. So let's put our examples on the other side for now. So let's say, first example, h of s is 1 plus s over 2 times 1 plus s over 3. So we want to do the Bode plot of this transfer function. Let's do it together. So we'll do a big one where we have plenty of room to do stuff and keep things clean. So again, 20 log base 10 of magnitude of h of j omega and phase of h of j omega. Okay, so we want to now use the rules that we've devised to do this without having to calculate it every time. So we have three terms. We have 1, 0, and 2 poles. Right? But we know something about the Bode plots. The Bode plot is the aggregate of these three because these are basically just getting multiplied. You can think about them as three systems in cascade that have, one has the 0, one has a pole, one has the other pole, right? So we can actually look at them independently and then do the aggregate of all three. So how do we do that? Well, first of all, let's look at it at very low frequencies. So what do each one of them give us? So let's look at the asymptote associated. Well, let's make this a little bit different. This is, sorry, let me make it 10 and 100. It would be easier to look at. Otherwise, it would become a mess. So what does the first, let me just do a color code on these two. Let's see. So I'm going to pick different colors. I don't know. S plus 1, S plus, or S over 10 plus 1, and then S over 100 plus 1. So what are the asymptotes associated with S plus 1? What are they? So what are the asymptotes? So we, at very low frequency, we've done this, right? This is that case. This is case number 2, the one with 0, right? So how does that look like? What are the two asymptotes? Yeah, so what would it look like? So at S, let's say omega being 1 of omega 1, let's put it here. So let's say this is 1. Well, log of 1, really. So this is omega of 1. At this point, you have something that basically comes in and goes up. So these are the two asymptotes, right? That's what we had here. So these are the two asymptotes. And then what else do we have? So, except for the fact that I used the wrong color. So, and what is the slope? What is the slope? Plus 20 dBs per decade. Okay, now let's look at the next one. How about the blue one, the denominator term? How does that look like? So what would it be? How does it look like? So again, you start from, so this is 0 dB, by the way. So you start off from here, and then let's say this is omega equals 10. What happens at this point? I have another asymptote that goes down, exactly. Right? With what slope? Negative 20 dBs per decade. And then I have that last one, which does what? Again, it keeps going. These are the asymptotes up to the point where I get to omega equals 100. And what happens at that point for that? Also goes down, right? With the same slope. Negative 20 dBs per decade. So the magnitude part of my Bode plot is really the sum of these three, the asymptotes, right? So what are the asymptotes like if I were to do this? So up to here, I have 0, so it keeps going up. And then when you hit here, you become flat because you have this adding to that, right? And then when you get to this point, to omega of 100, you start dropping at negative 20 dBs per decade. So this would be a plus 20 dBs per decade. So the actual plot will look something like this. If you really wanted to plot it, go like this, and then it would become flat, and then it goes there, and then it's just dropping. This is a little bit closer. So what does this tell you? Now, this is just maybe an exercise. Well, what is this for? What does it do, right? What does it tell you? It tells you that at frequencies below omega 1, this system does nothing to them. The output frequency and the input frequency have the same magnitude. So it doesn't attenuate anything, right, or amplify. As you go above between 1 and 10, you start amplifying. You're getting more. The gain is increasing. You're getting more at the output than the input. There's some amplification. Something is happening before the voltage. Then you have a kind of a flat region between 10 and 100. And then after that, you start dropping. So then you start having, at very high frequencies, the system's gain starts dropping below 0 dB, and then it goes down. Keeps going down. So at very, very high frequencies, it also attenuates. How about the phase part? Well, we know for the phase part, we have to look a decade below to a decade above. So this is like 0.1, and this is like, let's see, omega of 1,000. The green one's really dying. Okay. And then you start off from here. So if you look at the asymptotes of the first, what is that? Or where does it go from here? So this is like plus 90 degrees, negative 90 degrees. What happens to the phase? So you start off from here. What is the phase at this point? If you didn't have any phase contribution from anything else, just due to the term in the numerator. 45 degrees, right? So you only had that term, so you go from this point to that point to 90 degrees, right? Here. So this would have gone straight through that point to 90 degrees. However, now once you get to this one, the effect of this blue one is that its phase starts dropping these things now. What color did I use for the first one? Purple? Okay, let me just use purple for that. Okay, so that would have been by itself what you get from that guy. But now you also have the effect of this blue one. So the blue one starts a decade below to decade above. It goes from 0 to negative 90. So it goes from here to there. And then you have also the red one. And the red one, again, starts from a decade below its cutoff frequency to a decade above its cutoff frequency. So it starts from here going to its own negative 45 and coming down. So what is the sum of these three? The sum of these three in phase looks like this. So you start off from here. You go up, 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 till this kicks in. Then it becomes flat because these two start canceling each other, right? The purple and the blue start canceling. So you remain at 45, kind of. And then you start going down because now these two had canceled each other, but now you have the red one too. So it starts coming in. And where does it end up? How low will it go? What are the final values of these three? The final value of the pink one, the purple one, is 90 degrees, plus 90. The final value of these two, the red and the blue, are negative 90. So what is the total phase that you get at very high frequencies? Negative 90, right? 1 plus, 2 minuses. So you go down all the way to negative 90 degrees. So that's the phase response. So that tells you that as the amplitude is increasing, also phase starts leading first, become positive, and then it goes back to 0, and then it goes lagging. If you look at the phases of the sinusoids, you will see that for a system like this, just like the output starts getting ahead, and then it goes back, falls behind as you increase the frequency. Okay? Any questions? No. All right. So these are all good and nice, but there's one more thing we need to learn. There's one more element we need to add, and that would allow us to deal with everything. Because you remember, the systems that we had, we said if you want to keep the coefficient of the polynomials real, you will get first order and second order polynomials, right? So what do you do with second order system? So with second order systems, the form, for example, let's say you have a second order pole. So you can write it in the following form. 1 over q, omega over omega n, and this is the form we've seen before. Omega squared over omega n squared. So, or let's say S for now, S squared. So this is h of S. And therefore h of j omega would be what if this is h of S? This is the quality factor, and this is natural frequency. So what is h of j omega? Well, this gives you S squared, gives you j omega squared. J squared gives you negative 1. So you get a real part that's 1 minus omega over omega n squared plus j over q omega over omega n. So how does this look like? Well, let's look at the three asymptotes associated, the two asymptotes associated with this, not three asymptotes. So what happens is that if you're looking at log of omega, and then 20 log base 10 of magnitude of h of j omega, and phase of h of j omega, what do you see? At very low frequencies, what do you see? If omega is very small. So none of these two matter, so you have 1. So you get 0 dB. You start off at 0 dB. So this is one of your asymptotes, 0 dB. What about very high frequencies? At very high frequency, which term dominates? This term, right? The highest order term, which is this term. So you start dropping at what rate? At like an omega squared or S squared, which is what rate? What is the rate of drop here? If it's n is 2, or more accurately negative 2, negative 40 dBs per decade, right? Negative 40 dBs per decade. Now, so you have these two asymptotes. So it seems that, okay, well, it looks like this. So if you plot it this way, these are the two asymptotes. Well, okay, maybe my Bode plot looks like that. It's all good and nice except for around this point, which is, this point is actually omega n, right? But at that point, something interesting happens. So what if omega is omega n at that exact point? So when omega is, let's say equal to omega n, what happens to this transfer function? This term disappears. The real part disappears. So what you're left with is going to be 1 over this, which I can write as negative j q omega n over omega n, which is 1. This ratio is 1 at omega equals omega n. So it becomes negative jq. And what is the magnitude of negative jq at that frequency? So this is omega n, really. What's the magnitude of that? What's the magnitude of this? Q. So the magnitude is not 1, it's q. So if you have a quality factor of 10, let's say, what happens is that at this point, it's up here. So the actual Bode plot for a second order system does this. This part of it didn't come out nice. Yeah, that's better. And this height is q, or on this plot it's going to be 20 log of q. So if you have a quality factor, the amount of peaking that you have is actually basically tells you is a measure of the q of the system, the quality factor. How about the phase? Well, we know the phase at this point is negative 90, right? It's negative j. So at this point is negative 90. So it transitioned from 0 to negative 180, because at very high frequencies you get negative 180, because this is the only dominant term. But how fast it transition is a function of q. So as your q increases, this transition happens steeper and steeper. So as q is increasing, this becomes a sharper and sharper transition, which is the nature of resonance. Okay? So this is the other remaining part of those things. So if you have these 4 things, really, you can determine everything, the Bode plot for anything. And once you do several examples and exercises, you will get a better sense. Any questions? Okay. All right, let's take a quick break.